In this lecture, we are going to discuss about the structures and geometry of oxyacids of chlorine. So we know the oxyacids of chlorine. There are four oxyacids of chlorine: hypochlorous acid (HClO), chlorous acid (HClO2), chloric acid (HClO3), and perchloric acid (HClO4). In these oxyacids of chlorine, the oxidation of chlorine is increasing from +1 to +7. In hypochlorous acid, oxidation state is +1. In chlorous acid, oxidation state is +3. And in next oxyacid, it is +5 and +7. Now, when hypochlorous acid loses the proton, it gives hypochlorite ion. Chlorous acid loses the proton, it gives chlorite ion. Similarly, chlorate ion and perchlorate ion. So we want to discuss the structures of this oxoanion: hypochlorite ion, chlorite ion, chlorate ion, and perchlorite ion. Now, structures of these oxoanions can be explained on the basis of valence shell electron pair repulsion theory. The theme of VSEPR theory is to predict the shape of the molecules. On the basis of the VSEPR theory, we can predict the shape of the molecule and also the geometry of the molecule. Now, the geometry of the molecule, it is depends upon the number of bonding pairs and lone pair electrons in the valence shell of the central atom in that molecule. So according to the VSEPR theory, the number of lone pairs and bond pair electrons in the molecules are arranged in such a way that they remain as far apart as possible from one another to minimize the repulsion. So exact location and exact presentation of that lone pair electron is important in that molecule. So the correct position of the lone pair is very important. So to predict the shape of molecules using VSEPR theory, some steps are important here. First, write the Lewis dot structure of the molecule. Second, find the number of bonding pairs and lone pair electrons in the valence shell of the central atom. Third, counting the number of bonding pairs and lone pair electrons. Treat multiple bonds if they were single bonds. From the number and type of electron pairs in the valence shell of the central atom, predict the approximate shape and bond angle. Find the steric number. Steric number is the number of atoms bonded to the central atom and number of lone pairs of electrons with the central atom. Now, the general formula to predict the steric number, it is ABM-EN, where A is the central atom, B is the other atom linked to the central atom, E is the lone pair of the electrons. So steric number, it is ABM-EN, where M, it is the number of these other atoms attached to the central atom. N is the number of lone pair electrons, where E represents the lone pair of electrons. So steric number, it is equal to M plus N. So let us take some few examples to find out the steric number. Take some examples to find out the steric number here. See, first molecule I would like to take here, CH4 molecule. Let us represent the Lewis dot structure of this molecule. Carbon is having the electronic configuration 1s2, 2s2, 2p2. Valency is 4. So let us write here 4 valency Lewis dot structure. 4 hydrogen atoms are covalently bonded to the carbon atom, central atom. Okay. So this is the Lewis dot structure. Pair of electron form one covalent bond. So there are 4 pairs, forms 4 covalent bond. So to find out the steric number. Steric number, it is equal to the molecule, it is ABMEN. So steric number, it is M plus N here. Now actually this molecule, it is not having any lone pair of electron. All the electrons are bonding pair electrons. So number of bonding pair electrons is equal to number of bonding pair electrons. It is equal to, so 1, 2, 3, 4, 4 bonding pair electrons, and no lone pair electron is there. So this part is not there, no lone pair electron. So number of bonding pair electrons are equal to 4. This is AB4 type of the molecule. And for AB4 type of the molecule, the predicted geometry is tetrahedral. For AB4 type of the molecule, the predicted geometry is tetrahedral. That is, we can represent this molecule in this way, AB4, like this. So in this way, on the basis of the VSEPR theory, we can predict the geometry of the molecule. Actually, this molecule is not having any lone pair of the electron. But consider the another example, water molecule, second, water molecule. So in water molecule, let us write the electronic dot structure. So water molecule, suppose that's HOH. Okay, oxygen is having the valency 6. Each hydrogen atom is having 1 electron. Okay, so you can see there are 2 covalent bonds. So number of bonding pair electrons are equal to, number of bonding pair electrons are equal to 2, and number of lone pair electrons are also equal to 2, this 2 and this 2. So the steric number, it is equal to, now water molecule is belongs to which type of the molecule? According to this formula ABMEN. So it is, water molecule is belongs to AB2E2 type. 2 lone pair of the electrons are there. So water molecule, it is belongs to AB, because 2 hydrogen atoms are there, and E2. So steric number, it is equal to this 2 plus this 2. So as the steric number is 4, the expected geometry of the molecule, it is tetrahedral. But oxygen atom, it is carry the 2 lone pair of the electrons. So in the structure, we have to represent the correct position of the lone pair of the electrons. Okay. Now we want to discuss here the structure and geometries of oxoanions. Structure and geometries of oxoanions or oxyacids of chlorine. So first it is hypochlorite. First one, it is hypochlorite. So let us discuss the structure of hypochlorite on the basis of VSEPR theory. So this is hypochlorite ion, ClO minus ion. It is obtained from hypochlorous acid, HClO. When it is dissociated, this anion is formed. Okay. So let us represent the electronic dot structure. Oxygen having this electronic configuration 2s2 2p4. Number of valence electrons are equal to 6. Chlorine, number of valence electrons are equal to 7. So in this hypochlorite ion, according to the electronic dot structure, this is the electronic dot structure. Valency of chlorine is the central atom here, and valency of the chlorine, it is 7. So 7 electrons are there. And valency of oxygen, it is 6, but 1 electron is extra due to this negative charge. So that electron will be here, and it will carry the negative charge. So number of bonding pair electrons, only 1 bonding pair electron is there. So number of bonding pair electrons are 1. Number of lone pair electrons on the central atom, 1, 2, 3. Therefore steric number, it is equal to 1 plus 3. So this is the molecule of the type ABE3. Number of lone pair electrons are equal to 3. So AB3 type of this molecule. So as the steric number is 4 suggests that the expected geometry of the molecule, it is tetrahedral. So let us try to draw the tetrahedral geometry, tetrahedral shape, tetrahedral structure of the molecule. On the basis of the VSEPR theory, from the steric number, the predicted geometry is tetrahedral. So in hypochlorite ion, there are three lone pair electrons, 1, 2, 3, three lone pair electrons onto the chlorine, and only one bonding pair electron. That is, there is only one bond. Okay, so the three lone pair electrons at the three corners of the tetrahedron, and one the oxygen atom which is bonded to the chlorine, it is at the one of the corner of the tetrahedron. So the position of the lone pair of the electrons in such a way that there is a minimum repulsion. So the actual geometry of the molecule, it is linear. Okay, only one bonding pair electron, only one bonding pair electron is there. So only one bond is there. So it is having the linear geometry. That is, hypochlorite ion is having the linear geometry. On the basis of the VSEPR theory, we have to represent the lone pair of the electrons in the geometry of that molecule in such a way that there is a minimum repulsion between the lone pair electrons. So it does not affect onto the bonding pair electrons. So it is having the linear geometry. So the presence of the lone pair of the electron predict the geometry of the molecule. So this is about hypochlorite ion. Expected geometry, it is tetrahedral, but actual geometry, it is linear. Bond angle, it is 180 degree. For linear geometry, the bond angle, it is 180 degree. Now let us take the second example here. And that second example, it is the second example, it is chlorite ion. Chlorite ion. So second one, it is chlorite ion, ClO2 minus. This is chlorite ion. One oxygen is now additional. Let us represent the electronic dot structure. So chlorine is the central atom and two oxygen atoms as like of this. Valency of chlorine is 7. So let us represent 7 valence electrons are there. Okay. Valency of oxygen, it is 6 here. So 1, 2, 3, 4, 5, 6. This oxygen, it is having also 6 electrons, and 1 electron is extra due to this negative charge. It carries the negative charge. Now we represent here 4 electrons. So I would like to represent the 7 valency of the oxygen. So correct structure can be represented in this way. 2 electrons will be here. Okay. 2 electrons will be here. So 2 plus 2 plus 2, 6, and 1 electron will be here. So how many number of the bonding pair electrons are there? This can be represented in this way also. Okay. So you can see here, oxygen, these electrons, lone pair electrons, then this chlorine, these 2 electrons are donated to the oxygen. Chlorine is less electronegative than oxygen. So these 2 electrons are given out. So involved into the bonding pair. So there is a formation of the bond. And you can call this bond, it is a coordinate covalent bond. Okay. So these electrons are remains as it onto the chlorine. Now there is a one bond here with the neighboring oxygen atom, and these are the electrons of the oxygen, carry the negative charge. So this is the electronic dot structure. So on the basis of this electronic dot structure, now we have to find out the steric number. To find out the steric number, first of all, find out number of bonding pair electrons. Number of bonding pair electrons. Okay, number of bonding pair electrons. So it is equal to. So this 2 and this 2. Number of bonding pairs equal to 2. Number of bonding pair electrons are equal to 2. This is one pair, this is one pair. Second, number of lone pair electrons on the central atom, chlorine. Number of lone pair electrons onto the chlorine, this one and this one, it is equal to 2. Okay. So it means that this hypochlorite ion, as per the electronic dot structure, this is belongs to the type A, B, 2, E2, AB2, E2 type of the molecule. Lone pair electrons are 2. Okay, and steric number it is equal to this 2 plus this 2, it is equal to 4. So for steric number 4, the predicted geometry is tetrahedral. The predicted geometry is tetrahedral. So let us try to draw here the predicted geometry. Chlorine is the central atom. Okay, so suppose that one oxygen will be here, then two lone pair electrons are there, so one lone pair will be here, another lone pair will be here, and this is the oxygen atom. So there is a two bonding pair electrons, so lone pair electrons are here, okay, at the two corners of the tetrahedron. So these lone pair electrons causes the distortion in the molecule. These lone pair electrons causes the distortion in the molecule, because these bond pair electrons are shifted. Repulsion will be takes place here between the lone pair and bond pair electrons. So due to the repulsion, the bond angle will be here, bond angle will be changes. So therefore in chlorite ion, the bond angle will be changes. So it is having the angular shape. So we can represent the shape of the molecule in this way. Okay. Chlorite ion, it is having the angular shape with bond angle, it is equal to the bond angle in this molecule, it is around 110 degrees centigrade. Little bit change in the bond angle is there due to the presence of this lone pair of the electrons. Because at the two corners of the tetrahedron, as there is a lone pair of the electron, so lone pair causes the distortion to the molecule. So the correct geometry of the molecule can be represented in this way. Okay, this is the correct geometry of the molecule. So the presence of the lone pair of the electron causes distortion in the molecule, and the geometry of the molecule will be changes. So in this case, it will be changes from tetrahedral to angular. So actual geometry of the perchlorate ion, it is angular geometry, and steric number it is equal to 4. So this is for chlorite ion. This is for chlorite ion. Now let us take the another example here. Third example now I would like to discuss. Okay, remember the first two oxoanion. First one, it is ClO minus, it is having linear geometry. Second one, it is ClO2 minus, it is having angular geometry. Okay, in both the cases, steric number it is equal to 4. Steric number it is equal to 4. Now let us consider the third example for the oxoanion, oxyacid of the chlorine, ClO3 minus. Chlorine is the central atom. It is having 7 valence electron, and oxygen, it is the atom which is attached to the chlorine. It is having 6 valence electrons. That is known to us according to their electronic configuration. So now draw here the electronic dot structure of this chlorate ion. The name of the ion, it is chlorate ion, where chlorine is the central atom and oxygen atoms are bonded to the chlorine atom. So first of all, according to the VSEPR theory, we have to draw the Lewis dot structure of this. Lewis dot structure. without drawing the Lewis dot structure, we cannot predict correctly the expected geometry of the molecule. So as chlorine is the central atom and three oxygen atoms are bonded there to the chlorine. So 1, 2 and 3, three oxygen atoms. First of all, represent the electrons onto the chlorine. 7 electrons are there, so 2, then 2 electrons here, okay. Then on this side, the 2 electrons are there and 1 electron is here. Then oxygen is having how many electrons? 6. Valency will be 6 there. So we can represent the 6 electrons. This extra electron, it is due to the anion, this negative charge. Okay. Remaining oxygen does not having that type. So 1, 2, 3, 4, 5, 6. Similarly here. 1, 2, 3, 4, 5, 6. Okay. So this is the Lewis dot structure. Now how many bonds are formed here? So we can predict the bonded structure. So these electrons are donated to the chlorine. There is a donated to the oxygen. There is a formation of the coordinate bond. So here also the same thing, formation of coordinate bond. These electrons are donated to the oxygen. Now this is the covalent bond. So let us represent covalent bond. Okay. So we can represent the electronic dot structure of this. Okay. So see here. This is the electronic dot structure or Lewis dot structure. Now number of bonding pair electrons. Number of bonding pair electrons. So number of bonding pair electrons, it is equal to, or number of bonding pair, it is equal to. So this is 1, this is 2 and this is 3. 2, 2, 2 means 3 bonding pair electrons are there. Then number of lone pair electrons. Number of lone pair electrons. Number of lone pairs on the chlorine. So number of lone pair on the chlorine, now only remaining is 1. Okay. This is involved into the bonding, this is involved into the bonding, and this electron is also involved into the bonding. So lone pair is 1. So steric number, it is equal to, therefore steric number, it is equal to 3 plus 1. So here number of bonding pair electrons are equal to 3 and number of lone pair equal to 1. Steric number, it is 4. So what is the type of this molecule? A, B, 3, E. Okay. Lone pair electron only 1. So type of the molecule, it is AB3E type. And steric number 4 suggests that the expected geometry of the molecule will be tetrahedral. Now in this molecule, we have to represent the lone pair of the electron at the correct position. So in perchlorate ion, in chlorate ion, there are 3 bonding pair electrons and 1 lone pair electron. Steric number is 4 suggests that the probable geometry is tetrahedral. But on the basis of the VSEPR theory, the presence of 1 lone pair directed towards one of the corners of the tetrahedron. Directed towards one of the corners of the tetrahedron. So let us going to be represent this. Chlorine is the central atom. Only 1 lone pair of the electrons, so that lone pair will be here at one of the corner. 3 oxygen atoms are there, so it is at this corner, it is at this corner, and another oxygen atom, it is at this corner. Okay, so we can represent the shape of the molecule in this way. Shape of the molecule can be represented in this way. It is having tetrahedral shape. If we join this, it is having the tetrahedral shape. Okay, so number of bonds are equal to 3 between the chlorine and oxygen. So we can represent this. Okay, so this is the tetrahedral geometry. Now, due to the presence of the lone pair of the electron, it distorts the geometry. Distorts means the shape of the geometry is little bit changes because there is a lone pair and bond pair repulsion. As these bonds are there, so lone pair bond pair repulsion will be takes place. So therefore, the geometry of the molecule, it is trigonal pyramidal structure. Trigonal pyramidal trigonal pyramidal structure. It is having trigonal pyramidal structure. Okay. Trigonal pyramidal structure. So this is suppose that pyramid here and trigonal 1, 2, 3. So its structure can be represented in this way. Carry one lone pair electron like this. Okay, trigonal pyramidal structure it is having. Thus, in this way, we explain the structure of chlorate ion ClO3 minus, which is also having the same steric number here, but the molecule it is Ab3E type. Ab3E type. Okay, where there is only one lone pair of the electron and there are three bonding pair electrons. Now, the last oxoanion of chlorine, that is perchlorate ion. So let us going to explain the structure of perchlorate ion here. Okay, perchlorate ion. Fourth now it is perchlorate ion. So perchlorate ion can be represented as in this way: ClO4 minus. Chlorine is the central atom. Chlorine is the central atom. So in the perchlorate ion, the Lewis dot structure I would like to draw here. Lewis dot structure. 4 oxygens are bonded to the chlorine. Chlorine is the central atom. So Lewis dot structure will be in this way. Chlorine is the central atom. So represent the electrons of the chlorine. 7 electrons are there. Okay, 7 electrons are there in the valence shell of the chlorine. Oxygen, 4 oxygen atoms, one will be here, one will be here, one will be here, and last one will be here. So represent the valency of the oxygen. There are 6 electrons. Similarly here there are 6 electrons. Similarly here there are 6 electrons. Okay, and there are 6 electrons, but 1 electron is extra due to this negative charge. Due to this negative charge, this oxygen is having the extra electron. So on the basis of this electronic dot structure or Lewis dot structure, we have to find out here number of bonding pair electrons, or the same structure can be represented in this way also. Chlorine, these electrons are donated to the oxygen, formation of one bond. Similarly here, formation of the one bond. Similarly here, formation of the one bond. These electrons are donated to this oxygen atom. Now there is a formation of this covalent bond. Okay, formation of the covalent bond which carry the negative charge. So after the representation of this, we can write here number of bonding pairs. Number of bonding pairs. So you can see the all are the bonding pairs 4. Okay. Number of lone pairs. Number of lone pairs. So electronic dot structure shows that there is a no lone pair onto the chlorine. No lone pair is here now. All the electrons are involved into the bonding. Okay. This one, this one, this one, and this. So 0. So steric number it is equal to this plus this, it is equal to 4 plus 0, it is equal to 4. So this is the molecule of the type AB4. Now lone pairs are not existing there, so no E is there. AB4 type of the molecule. So for AB4 type of the molecule, the predicted geometry is tetrahedral, and for steric number 4 also the predicted geometry is tetrahedral. So as there is no lone pair of the electron, So there is a no repulsion. So in perchlorate ion, there are 4 bonding pair of electrons and no lone pair of electrons. On the basis of the steric number, the predicted structure is tetrahedral. Since perchlorate ion has no lone pairs, there is no distortion. No distortion in the molecule. Okay. Hence, perchlorate ion has tetrahedral geometry. Perchlorate ion has pure tetrahedral geometry. Okay. It is having pure tetrahedral geometry. So it can be represented in this way, tetrahedral geometry. So chlorine is at the central, 4 oxygen atoms are there at the 4 corners of the tetrahedron. Okay, so 4 bonds are there. So let us represent the 4 bonds. Okay, and if you join this as like of this tetrahedral geometry. Okay, so this is the expected geometry, or it is also represented as in this way, this oxygen. Okay, like this. So this is the one oxygen carry the negative charge. So this is the geometry of the molecule. It is having tetrahedral geometry. So thus on the basis of Hess EPR theory, we can explain here the structures of oxo anions of the oxyacids of the chlorine. Oxo anions of oxyacids of the chlorine. Okay. So for oxo anions we have taken, first one it is chlorite, hypochlorite, second one it is chlorite, third one it is chlorate, and fourth one it is perchlorate ion. Okay. In all the ions, the number of the steric number is same, but number of lone pairs and bond pair electrons are different. So thus in this way, in this lecture, we have explained the structure of oxo anions or structures of oxyacids of the chlorine, where chlorine is the central atom and oxygen atoms are the atoms who are bonded to the chlorine. So on the basis of the Lewis dot structure, we can represent the structure of these oxyacids of the chlorine. Right. So this is about the structure of oxyacids of the chlorine.